Azure Container Instances, ACI, is a managed service that enables the rapid deployment of containers without needing to configure or manage underlying virtual machines or additional infrastructure. Within the broader context of Azure Compute Services, ACI offers an optimal solution for scenarios that do not require the orchestration complexity of Azure Kubernetes Service, AKS, but still demand isolation and consistent performance. By focusing on container-level deployment, ACI makes it possible to build and run applications in a lightweight environment, streamlining the development lifecycle. This approach aligns with previous topics on resource provisioning, as containers can be deployed using Azure Resource Manager, ARM, templates, or bicep files, reflecting best practices learned throughout the course. Whether used for batch processing, event-driven workloads, or hosting microservices, ACI simplifies the container journey while enabling you to leverage Azure's mature ecosystem of networking, storage, and logging services for a complete compute solution. In the context of Azure's extensive compute ecosystem, Azure Container Instances occupies a vital role by offering a flexible, consumption-based model for containerized workloads. Unlike Azure Virtual Machines or Azure Virtual Machine Scale Sets, ACI does not demand extensive configuration of the underlying operating system or the VM infrastructure. This characteristic supports the shift from monolithic to microservices architectures, where containers operate independently, yet can be seamlessly integrated. Moreover, ACI fits between fully orchestrated solutions, like Kubernetes, and traditional VM-based deployments. For smaller-scale tasks or on-demand services, it delivers the right balance of agility and control. By focusing on single container or small multi-container scenarios, administrators benefit from a simplified approach while simultaneously maintaining consistent policies and resource governance across Azure resources. This positioning underscores how ACI complements existing compute frameworks and fosters continuous improvement in development processes, aligning with the course's overarching goals of efficient and well-managed Azure deployments. Azure Container Instances provide several critical features that make them a compelling option for running containers at scale. First, the service offers granular cost control, since billing is based on the number of vCPUs and memory actually consumed by the container during its active lifetime. Second, ACI supports both Linux and Windows containers, ensuring broad compatibility with different application stacks. Third, the platform integrates seamlessly with Azure Container Registry for secure and private image hosting, as well as public registries like Docker Hub. Multi-container groups enable lightweight container orchestration by allowing related containers to share local network and storage resources. Additionally, ACI simplifies operational tasks by removing the need for manual patching or cluster maintenance, a key difference from self-hosted environments. These advantages position ACI as an ideal solution for burst workloads, continuous integration pipelines, and rapid prototyping, thus allowing administrators to accelerate time to market without incurring unnecessary infrastructure overheads. Before provisioning a container with Azure Container Instances, it is essential to plan and prepare the container image. This includes choosing the appropriate base image tailored to your application's runtime or operating system requirements. If your application is developed in .NET Core, Node.js, or Python, for instance, selecting a lightweight base image reduces resource footprint and startup times. Next, ensure that the Docker file is optimized, avoiding unnecessary layers by combining commands and removing extraneous dependencies. Clear versioning and tagging strategies help maintain consistency, particularly when referencing images from Azure Container Registry or other repositories. Additionally, security best practices, such as scanning for vulnerabilities and applying recommended updates, enhance runtime reliability. The integration of these practices aligns with earlier course topics, complementing steps taken when deploying infrastructure via ARM templates and Bicep, ensuring that containerized workloads are properly aligned with your organization's broader compliance and governance standards. Azure Container Registry, ACR, is a managed, private Docker registry service that securely stores container images for deployment across Azure. By hosting images in ACR, organizations benefit from a centralized catalog that simplifies version management and ensures consistent deployment. ACR integrates smoothly with Azure Container Instances, providing rapid image retrieval with reduced latency. Administrators can configure a dedicated repository within ACR to maintain controlled access, leveraging role-based access control, RBAC, to grant or revoke permissions. Additionally, the platform offers capabilities like Content Trust, which validates image integrity, and scanner integrations for detecting vulnerabilities. Integrating ACR with Azure's pipeline services, such as Azure DevOps or GitHub Actions, further automates the image build and push process, aligning with the infrastructure as code mindset established in earlier units of the course. This synergy between ACR and ACI results in a robust solution that streamlines container provisioning, fosters collaboration, and maintains enterprise-level security standards. Provisioning a container in Azure Container Instances via the Azure portal offers a user-friendly approach to deploying and managing containers. After logging into the portal, navigate to the Azure Container Instances blade and select the desired subscription, resource group, and region. Provide a container name, choose the image source, such as Docker Hub or Azure Container Registry, and specify vCPU and memory allocation. ACI simplicity is evident as administrators configure networking, either opting for a public IP address to expose the container externally or integrating with a virtual network for private access. Once the container's advanced settings are configured, including mounting volumes or specifying environment variables, the portal presents a summary of the settings. Clicking Create triggers the background provisioning process, which typically completes within seconds to minutes. This streamlined experience caters to both beginners and experts, showcasing how ACI delivers a highly efficient route toward container-based application delivery. For administrators seeking automation or repeatable processes, provisioning an Azure Container Instance via command line interfaces such as Azure CLI or PowerShell is advantageous. This approach aligns well with infrastructure as code principles outlined in previous course modules. With Azure CLI, for instance, the AZ Container Create command offers parameters to specify resource group, container name, image, and CPU memory specifications. Environment variables and port mappings can be provided directly in the command or via configuration files. Similarly, PowerShell commands provide scriptable options that fit neatly into deployment pipelines. By embedding these commands within a continuous integration or continuous delivery workflow, teams can programmatically scale their container operations while maintaining consistency. Additionally, these scripts can reference ARM templates or bicep files to outline more complex topologies, effectively bridging container deployments with broader infrastructure components. This method thus grants granular control over container configuration and fosters sustainable, version-controlled provisioning processes. Once containers are running in Azure Container Instances, proper configuration and resource management ensure stable and predictable performance. Administrators can allocate CPU and memory resources according to workload requirements, preventing overallocation or underallocation that lead to inefficiencies. ACI enables updates to container definitions, letting you adjust environment variables or mount additional volumes. These changes can be made through either the portal or command line, reflecting the flexibility introduced in prior modules on Azure Compute Management. Regularly inspecting resource usage and adjusting quotas is advisable, particularly when workloads scale or transition. Additionally, deploying multiple containers within a container group allows them to share life cycles, networking, and volumes. This structure proves beneficial for sidecar patterns or containers that must communicate internally. By combining resource governance techniques, environment variable encryption, and role-based access control policies, administrators can uphold the operational standards recommended throughout the AZ-104 course while maintaining streamlined container deployments. Networking in Azure Container Instances provides connectivity for both internal-only applications and external-facing services. By default, ACI can assign a public IP address, enabling direct access over the internet. Alternatively, containers can be deployed into Azure virtual networks, facilitating secure communication with resources such as Azure SQL databases or application gateways within an organization's private address space. This integration leverages subnets and network security groups to enforce inbound and outbound rules. Meanwhile, role-based access control, RBAC, at the resource group or container level restricts unauthorized provisioning or configuration changes. Network isolation is further enhanced by specifying port mappings, ensuring that only intended ports remain accessible. Administrators can incorporate additional security measures, including service endpoints or private link, to further minimize exposure. By systematically managing network settings and access permissions, ACI becomes a credible choice for enterprise-level workloads requiring both scalability and stringent security postures, reflecting best practices in Azure Compute Management. Monitoring and logging capabilities are critical for diagnosing performance bottlenecks, tracking application behavior, and guaranteeing system health within Azure Container Instances. Azure Monitor natively integrates with ACI, offering real-time metrics such as CPU and memory utilization. Container logs can be viewed directly from the Azure portal or tapped via Azure CLI, and they aid in quickly identifying issues during runtime. For deeper insights, administrators can stream logs to Azure Log Analytics or use tools like Azure Monitor for containers. This approach provides centralized dashboards, query capabilities, and alerting mechanisms, which simplify proactive maintenance. Furthermore, distributed tracing can be achieved by integrating with application insights, enabling correlation of container-level metrics with broader application events. By consistently applying these logging and monitoring techniques, organizations can create a reliable, transparent environment that aligns with the governance and observability principles discussed in previous modules of AZ-104, ultimately streamlining support for container-based workloads. Although Azure Container Instances primarily supports single container or small multi-container scenarios, administrators can still leverage scaling strategies to meet demand fluctuations. One approach is to programmatically create and remove container instances via scripts or pipelines in response to queue messages or custom metrics. When a more sophisticated scaling mechanism is required, it is common to integrate ACI with Azure Kubernetes Service, AKS, through the Virtual Nodes feature, effectively offloading overflow pods to ACI for burst capacity. This hybrid approach combines the minimal overhead of ACI with the orchestration advantages of AKS. In terms of performance tuning, selecting the correct container size and distribution of CPU cores ensures that workloads achieve optimal throughput. Regularly reviewing logs and analytics helps identify patterns that warrant fine-tuning or more advanced strategies. These practices align with the course's emphasis on right-sizing Azure compute resources, underscoring the importance of efficient resource usage and workload performance. Azure Container Instances integrate seamlessly with various Azure services, broadening opportunities for building highly connected applications. Containers can securely interact with Azure storage, using persistent volumes to retain data between instance restarts. Their ability to connect to Azure SQL Database or Cosmos DB lends flexibility in data storage strategies. Additionally, event-driven architectures can take advantage of Azure Functions and Azure Event Grid to trigger container deployments based on specific messages, events, or conditions. For more advanced scenarios, ACI supports bridging into virtual networks, allowing containers to communicate securely with services hosted in Azure App Service or virtual machines. By leveraging managed identity, containers can authenticate to other Azure services without manual credential management, upholding core DevOps principles of security and consistency. These integrations speak to the broader course theme, constructing robust, end-to-end solutions in Azure that utilize containerization as a central pillar of modern cloud-native design. To secure and optimize container deployments in Azure Container Instances, conscientious adherence to best practices is indispensable. First, Always use minimal base images and apply timely patches to reduce the attack surface. Turn on vulnerability scanning through Azure Security Center or integrated third-party tools to ensure that images remain compliant with security standards. Next, store sensitive data, such as connection strings or license keys, in Azure Key Vault and reference them via environment variables. Network security can be enhanced by using lockdown subnets, NSGs, and private endpoints as needed. Enforcing role-based access control prevents unauthorized container creation or updates, complementing the principle of least privilege. Logging and monitoring should also be configured thoroughly to identify anomalies early. Lastly, adopt a consistent CI/CD pipeline that incorporates frequent image testing, scanning, and versioning. By integrating these considerations, organizations can confidently rely on ACI's convenience while sustaining the robust security posture advocated throughout the AZ-104 curriculum.